Why are they special? Why are they important? Why should you look at them compared to just MLPs with a single hidden layer? So we looked at some factors, some reasons why they're important. Uh, so one is that you get a good, elegant, structured, hierarchical solutions, right? Just quick recap. And so we saw the example of this parity problem, where if you have a 2-bit parity module, you can easily construct a network for any n bit or actually 2 power n bit parity in a problem simply by assembly of these units, right? And you get a good hierarchical representation where lower layers respond to simple features, simple local features, and higher layer respond to more and more complex features. This property is more relevant to image pattern recognition. So, and we also compared that similar organization also is seen in human visual system, which is a nice thing. Then we saw this theorem, which Hallstatt theorem, which says that in a Boolean network, if you have k layer, if it has k layers, and you use polynomial number of nodes, which has k layers, it might require exponential number of nodes with k minus 1 layers. So if you reduce the layers, you might still get a representation, but you might end up with a very large number of nodes. So sometimes using more layers can reduce the total number of nodes required. So then we also saw that it's gradient diffusion property. That is when you have too many G primes, right? So there is a wedge don't change much or slowly in lower layers. So that is good for transfer learning. So with all these features of deep neural networks, let us look at a special class of neural networks, of deep networks, which is a convolutional neural networks or CNNs, and how they are very good at classifying image patterns. So first of all, let us look at, because everybody uses the term convolutional neural network, let us define what is convolution. So in signal processing, we learned that this is what convolution is. If you have two signals or two functions, f and g, right, a convolution of these two functions is given by the integral, right, f of a times g of x minus a integrated over dA, right, and this kind of integral involving the two functions is denoted by the notation fx star gx, right, and this operation is commutative in the sense you can interchange the positions of the two functions in the integral and you get the same resulting function. A small numerical simulation to show how the convolution works. So basically you have to take one of the functions, flip it right in time or space or whatever is the axis, and then shift it by whatever amount. That the amount of shift is what is given by the variable a, right? And now in this new position, just multiply these two functions point by point and integrate that. So let's say g is what you have taken. You flip it and then shift it by x, and then multiply the two functions point by point. That is multiply f of a and g of x minus a, and integrate that product function. Right. So for example, in this case, so if you flip g and then shift it by x and just multiply them, since there's no overlap between these two functions, the result is 0. So for this value of x, the output is 0. So if you let us call output function like p of x. So p of x is 0 for this value. So it is for x is less than 0. Now for x between 0 and 1, now the two functions will have some overlap. And so you see that overlap area is shown in is colored in gray. And you can easily calculate that the integral now works out to be x by 2. So the resulting function is now a function of x, the shift value. So now for x between 1 and 2, again there is some overlap, and overlap is now 1 minus x by 2. Right. So then finally for x greater than 2, again the two functions don't have any overlap, so the resulting function is 0. So basically the resulting function p of x is equal to f of x star g of x is equal to 0 for x less than 1. Sorry, x less than 0. So it's what we worked out here. At x less than 0, it is 0. And x between 0 and 1, it is x by 2. X between 1 and 2, it is 1 minus x by 2. And beyond that, it is 0. So which is given in the function, the graph in the bottom. So that's how the convolution works in one dimensions. You can also do it in two dimensions, or in fact in any number of dimensions. And for two dimensions, you get what is called image convolution or 2D convolution. So if you want to convolve two functions w of x comma y and f of x comma y, all right, you flip f of x y, and then you get f of x minus, and then shift it by x and y respectively in the two dimensions. Then you have w of st, like two variables. Then f of x minus s and y minus t. You multiply this and sum it over the entire space of S and T. In this case, it's a finite space going from, say, plus k minus k by 2 to plus k by 2. It's a square of size k by k. So this summation gives you a result which is a function of x and y alone, and that is the new function g of x comma y. So so you convolve two images and you get a new image. Just to show an example, so I have what is called a kernel. So in case of convolution, you do convolution, but f of x y is an image and w of x comma y is actually an image, but it's a very tiny image. It's a matrix. It's called a kernel. And for example, you take a kernel like this, right? It has highest value in the center, and it's a 3 by 3 kernel, and so a bunch of numbers on the on the outer rows and columns. So now you move this kernel over the entire image, right? And at every position of the kernel, you just do the integral or do the summation. So how do you do that? In this case, you place this kernel over this bottom part of the image. You can see the kernel being placed in the bottom part of the image. You can also see that the part of the kernel is outside the image. So assume that once you are outside the image, the pixel values are all zeros, right? And at every position, you multiply the kernel value with the corresponding pixel value. So 52, 54, these are the pixel values, times 0, minus 1, 0, and all that. So you multiply like that. 50, these are pixel values. Minus 1, 5, these are all kernel values. So in this case, the part where you're outside the image, you imagine that is zeros. So 0 times 0, 0 times minus 1, 0 times 0. So you get some number. That number is the result of the convolution. Now that number is the value of the resulting image, which corresponds to the pixel value at this center of the kernel, because of which is shown here in the little red square in the right image. So like that, for every position of the kernel, you calculate one new pixel value, and you put that set that pixel value in the output image. So given this kind of operation, you can define a convolutional network. And again, let's go back to one of the first convolutional network implementation, which was developed by the for AT&T to read numerals, handwritten numerals on postal envelopes. So it goes something like this. So you at every point in the input image, you have so each. Let me see if I have a better. Yeah, so at so the first hidden layer consists of 4 sublayers, each of size 24 by 24, right? And this is called the convolution layer because a given neuron in this layer it connects to a small window of neurons in the or image pixels in the previous layer. So the same weight vector is copied at every position. That's why it is called a convolutional layer. Then from this first hidden layer to second hidden layer, when you go to second hidden layer, you simply compress the size of this each of the sublayers. So in this case, you go from 24 by 24 to 12 by 12, right? So each 2 by 2 window of this layer is compressed to a single pixel, right? By doing something called pooling. So I'll describe what is pooling in a minute. So all these 24 by 24 hidden sublayers in the first hidden layer are converted into 12 by 12 sublayers. So since you have 4 of them here, first hidden layer, if you have 4 of them, second hidden layer. After that, again, you will have like pairs of such convolution layers followed by pooling layers. After a bunch of such layers, you have what is called fully connected layers. So because until then, you have each hidden layer has a bunch of sublayers. Each sublayer is a 2D layer. And after a certain stage, you have simply a 1D row of neurons. And at this point onwards, you have fully connected, full connectivity. That is, every neuron in the previous layer is connected to every neuron in the next layer. So you will typically have a few layers like that, and finally you have output layer where you train the network to classify the input image, right, by in a one-hot fashion. That is, only one neuron is high, and other neurons are all low. This network gave excellent performance. You have seen this in the last class. Now, originally we said we'll use sigmoid functions because the original MLP theorem requires a function which has all those properties we looked at, right? Continuity, monotonicity, and boundedness and all that. So we use sigmoid because it is differentiable, and so although the approximation theorem doesn't need differentiability, your backprop algorithm needs differentiability, so we use that. So we also suggested that tan H is also good enough. But the point is, these are transcendental functions, and computation of this can be quite expensive. So people began using simplified versions of this, or rather piecewise linear versions of this, which are computation less intensive. Also, the sigma and tan H are bounded, so therefore you cannot get a big range of values in the output. So people found that another function called ReLU, which stands for rectified linear unit, which is given by max of 0 and x. It is for x positive, output is equal to x negative, output is equal to 0. So given by this graph. So usually in the hidden layers, you use ReLU function because you have greater range of variation of the output. And there's also something called a leaky ReLU. So where on the negative side, it's not completely 0, but it has a small slope. Then there's also something called ELU, which is a kind of a differentiable version of ReLU. It is smooth. It doesn't have this discontinuity in derivative right at the origin. Now we talked about pooling, where a kind of a, let's say 2n by 2n array is reduced to n by n size. And so what happens in case of there are several different kinds of pooling. The two are popular. One is what's called average pooling or mean pooling. This illustration shows how it works. So let us say you are going from a 4 by 4 array to a 2 by 2 array. So each you divide the 4 by 4 array into 4 2 by 2 arrays, and each 2 by 2 array you take the average of all the pixels and you put it set it to the corresponding pixel value in the output. So all the 4 blue pixels, right, average out to 5. The green pixels average out to 2.75, and so on and so forth. In case of max pooling, instead of averaging, you take the max value. So if you look at all the pixels in this yellow or orange area, the max is 6. So you put it here. In case of green, the max is 8. So put it here, and so on and so forth. So basically, the intuition behind max pooling is winner take all. That is, the winning neuron will get highest representation. Others who lost the competition are completely wiped out, or they are ignored. Right. So see, the idea is you want to design a network in such a way that distinct neurons respond to distinct patterns or distinct pattern classes as much as possible. Everybody responding to everything is not a good idea. Right? You want some kind of specialization to emerge as a result of training. So in this case, this neuron is responding with a 6 to some input pattern, or maybe to some part of the input image, right? And so you want to encourage that, and you want to suppress all the other guys are also responding, but they are not responding that well, right? So you suppress them, you neglect them, and you only give importance to this fellow who is already giving high response. Now, in the output, typically use something called Softmax principle, especially when you are using the network for classification. You could also be using network for regression. Then Softmax is not used. It has no meaning. So why is Softmax used? Suppose the total input. Let me see if I can write this down. So this is the output layer. The total input from the previous hidden layer into the output layer. You call this. So call this total input value. Let's say yi. Okay, so this is yn. then this could be any value, right, from large negative to large positive. Whereas if it is a classification problem, you want ultimately the outputs to look like 0, 1, 0, 0, something like that, right? Or at least if the mean probabilities, right, you want each of these, let's call them, let's say PIs. Okay, so the PI should be in the set 0 to 1. Okay, so how do you make sure that output comes in this comes into this range? So this is done by this formula. So basically, take the total input into each of the output neurons, call that yi, and then compute this expression e to the power of beta yi, which is for the ith output. So call this pi. Okay, and divide by sigma over all the same expression calculated for all the outputs. So one thing that this will give you is that sigma pi is equal to 1, which makes sense because input belongs to only one class. Right, ultimately probability for that class is 1 and all the other probabilities of all the other classes 0. But even if that's not the case, the probability should add up to 1. So that intuitive requirement of probabilities is satisfied by this formula. In addition, you can in other contexts use Softmax principle also in a kind of a actually probabilistic sense. That is, since you have this is a probability, the actual class is computed in a probabilistic fashion. And if B is a large positive number, the probabilities tend towards either 1 and 0, like to the extremes. Okay, so it becomes more and more deterministic. So, in fact, if B tends to infinity, this expression simply picks the highest y. It acts like arg of max y. So, if as B tends to infinity, okay, so Pi will tend to 1 for I corresponding to max y. Okay, so if I corresponds to max yi, then the corresponding pi will tend to 1. All the other pi's will tend to 0 for pj not equal to I. Okay, so this is a nice property. So this is the reason why people use Softmax principle. So let us look at one of the there are many nice success stories of CNNs. One classic example from 2011 is this CNN used for traffic sign recognition. So traffic signs look like this. This was, I think, a German group. That is, so they're taking such signs from Europe. So you need to you are given pictures of these traffic signs and you're supposed to classify them. The totally training set has 39,000 images and there are 43 classes. So all of these pictures look very clean in the ideal case. In real case, the pictures are actually very, very highly degraded, so poor quality. And so classifying them will be hard. Even for a human reader, this is quite hard. Because you should not only recognize that it's a speed sign, you should also say that it is 60 kilometer speed sign, 50 kilometer speed sign. So the class is very specific. And classes are not organized as a tree structure or anything. It's you have to specifically say that it is 60 kilometer speed sign, 50 kilometer speed sign, and so on. So it's quite a hard problem. And this is the kind of problem you will encounter if you are dealing with, for example, a driverless car. So in a driverless car, the driving system, what's called ADAS, right, we'll have to keep on analyzing the surrounding scenes and get all this information, constantly change its driving according to this feedback. So for example, if it sees a 50 kilometer speed limit sign, then it should slow down if it is going faster than that. So, so each image is of size 40 by 48 and it's a color image. So CNN uses a fairly large CNN. This is not a whole lot. I mean, there are other studies where people use like 150 hidden layers and so on. So in this case, the input is as three colored images, RGB, each of size 40 by 48. Then next is convolution layer has 100 sublayers. These are called the feature maps, each of size 42 by 42. So from there to the input, the kernel size, the weight kernel size is 7 by 7. So this is typically the format in which the CNN architecture details are given. But the specifications of the architecture are kind of given like this. Next stage is max polling. So note that it is max polling and not average polling. And typically max polling is used. Then again you have 100 maps because max polling is basically applied to each of the convolutional sublayers, convolutional for feature maps. So there's a one-to-one mapping between the convolutional feature maps and max polling layers. So it's a 2 by 2 kernel, therefore you go from 40 by 42 to 21 by 21. Okay, and then next again you have convolutional layers. So the typical trend is to increase the number of feature maps in convolutional layers and decrease their individual size. So here the size you start with 40 by 42, right? And next you reduce size in max polling, go to 21 by 21. In the next convolutional layer, they've gone from 100 to 150, but the size of the individual feature maps has gone to 18 by 18 from 21 by 21. And the kernel size here from the previous layer is 4 by 4. Then in the next max polling, you go from 18 by 18 to 9 by 9, again by using a 2 by 2 kernel. Right. Suppose you use 3 by 3 kernel, it will go to 6 by 6. Right. And so then you increase the number of hidden feature maps further 150 to 250 in the next convolution stage. Then the feature map has also gone down. Individual feature maps have gone down to 6 by 6. Then in max polling, same number of feature maps, but their size has gone down. Each of them is 3 by 3. So at this point, you see what is happening is you have 250 feature maps, which is a large number, but individual feature maps are very small, 3 by 3. It is almost like single neuron. So from this level, right, of 250 feature maps, each of them is of size 3 by 3. You straight away now go to, because there's no point in decreasing any further would mean like going to a single neuron. So you take 300 neurons here, and every neuron here is connected to every neuron in this feature map, and not only that, in all feature maps. So therefore you have full connectivity, and same story for all neurons. And after that, straight away you go to the 43 neuron output layer. So this is output, where each neuron corresponds to one class. And from this layer to output also, it is fully connected. Okay, or FC. So sometimes these feature maps are also shown as stacks like this, because drawing lots of squares next to each other will take too much space. So that is shown as a stack like this. So input is a stack of 3 images, 3 colored RGB. Then you have a stack of feature maps in the convolutional layer. Then you have a stack of reduced size feature maps in max polling, and so on and so forth. The stack size goes up. That is, the number of layers in the stack goes up, where the layer size goes down. So this picture shows the responses of various layers, or neurons in various layers for a given input. So input here is a speed limit sign. I think it's like 30 kilometers sign. Then the response of that image in the first hidden layer, which has 100 maps. So you see that from first input layer to the first hidden layer, the response still kind of looks like the input. It's just that it's either flipped and it's like a negative of that or something like that. But you can still see the outlines of the content of the input image. You can see that 30 kind of shape in all the responses. Now, once you reduce it further to 21 and 21, now the details are disappearing. But doesn't matter. It is constructing complex representations of the input, right? And as you go further, you cannot see. So the details of the input image fade away further and further, right? And as when you go here, this completely gone. So this network gave 99.46%, best among all the candidate algorithms. it was even better than one of the humans. So the same data set is given to a bunch of human subjects to manually classify. And of course, since humans are also different in the capabilities, different people gave different performances. And the network beat some of those people, so which is quite scary because so all the time we thought that there are certain things where humans are better than computers. Okay, and certain things computers are better than humans. Like for example, simple arithmetic operations involving large numbers. Computers are better than humans any day, unless you are Shakuntala Devi or somebody like that. But things like visual pattern recognition, we always thought humans are better than machines, especially with all the noise and so on. That's where humans are generally considered to be better. But even in such problems, now the CNN is beating humans. It is referred to as superhuman performance. Okay. Okay, and also it makes 3 times fewer mistakes than the second best algorithm, which is 98.31% accuracy. So a simple CNN can also be used to design a self-driving car or the system for self-driving car, right? And only thing is, in this case, the system only decides how to drive the steering. It doesn't control brakes. Somebody has to sit and control brakes. But in a more comprehensive system, you need to also control brakes. Right? In this particular example that I'm showing, it only controls the steering angle. So this system can drive a car under special conditions. Which can drive without lane markings on both local roads and highways. Can also operate in areas with unclear visual guidance. But like braking is separately controlled. So the hardware used is this NVIDIA dev box, which can run machine learning software. So the car has 3 cameras. One is in left, center, and right, and 3 measures are given as input to the CNN. CNN is a pretty large architecture here. So input is three measures of size that's 66 by 200, and then after that, it's lots of convolutional and hidden layer. There are no max pooling here. You just keep on reducing the size of the convolutional layers. And after that, you have a bunch of fully connected layers, right? And so what you do is, when you go from this last convolutional layer to the fully connected layer, this kind of a conversion. So we have seen that here also. We have 3 by 3 arrays, and there are 250 of them. So these are given as input to every neuron in the next layer, consisting of 300 neurons. So you basically imagine that this 3 by 3 times, so 3 by 3 times 250, right? You think of it as, I don't know what that is, 750 times 3, or whatever that is. So you think of it as simply a single row of that many neurons. So this step, just imaginary step, is considered flattening, right? You flatten these 2D layers into a long 1D layer. And then you feed that 1D layer of neurons as input to the next layer using a fully connected wait stage. So you have 1064 here and 100 neurons, 50 and so on and so forth. So the thing is, there's no sanctity to any of them. There's no secret formula that tells you what size to use. So basically, if the problem is more complex, you use more hidden layers, more convolution layers, and so on and so forth. But at trial and error, you have to decide and determine what is a good architecture for a given problem. So it's a pretty large network, 27 million connections and 250,000 parameters. Because what happens is there is something called weight sharing. So when you have a feature map, right, taking inputs from the input image, so each neuron gets input from an array in the previous image. So a neuron here gets input from here, neuron from here, neuron here gets input from here. So you see that there are 2 weight kernels here. This is W1, and let's call this W2. So thing is, if you want it to describe a convolution, the weight kernel used here and weight kernel used here must be the same. So that means W1 is equal to W2 is equal to similar weight kernels everywhere in the array. So only then you will call it a convolution. So by doing that, what happens is, although you have so many different weight kernels, they all have the same set of parameters. So therefore, although you have lots of, so you'll end up with a lot more connections than number of actual distinct parameters. So that's why in this network you have 27 million connections, but only 50,000 parameters, right? And so also when it comes to training the network, so what happens is to train the network, you have to actually take the car out. So a driver should sit in the car and drive the car around. And as the car is going around, the camera takes a video. The system also records the actual steering movements of the driver. And this will be used as, so the input video images and the steering angle outputs. These are used as training data for the system, for the CNN to train when you train it. But the problem is that data alone is not enough to train the system effectively, because most importantly, you need data corresponding to the case when the car veers off the road. Suppose by some for some accidental reason, the car veers off the road, right? How do you do a course correction and bring the car back onto the road? So that for the system to be able to do that, you need to have training images which correspond to the case when the car is off the road slightly. So they also use that kind of a synthesized data, right? Where the vehicle goes off the road and then there is steering is used to correct that situation and bring the car back onto the road. So you combine real videos with this kind of synthetic, problematic data and use it to train the network. So network performed very well. So the one way to judge the performance is in terms of something called autonomy. That is, so although the network is driven by the machine, this CNN, there will be a person sitting there in the driving seat, just to make sure if some untoward incident happens, they can react quickly and avoid the problem. So thing is, if they are intervening too often, then the system is no good. I mean, it needs too much of handholding. So that is described by a term called autonomy. That is how many times you have to intervene in the car's journey, right, as it goes on the road. So that is given by this formula. So 1 minus number of interventions times 6 seconds by total elapsed time. So total driving time. So the idea is that each intervention takes about 6 seconds, let us say. So the amount of time during which the car is driven by the human driver divided by total driving time, and 1 minus that gives you the level of autonomy that the car has achieved, or the car's navigation system has achieved. In this case, the system has achieved 98% autonomy. So you can see that even a very simple network, and it's complex only in size, but quite simple in its operation and the way you train it and all that. So that's a very interesting development, which shows that even a simple CNN can be used to solve a very complicated real-world problem. So next example we'll look at is again an example from medicine. Right here they use a CNN to do mitosis detection, right, in breast cancer histology images. So in cancer, as you know, is a case of high cell growth or high tissue growth. High cell division rates are seen in cancer tissue. So high mitotic rate is a strong indicator of cancer tissue, and therefore in a histological image, that is, you put these cells in a slide and look at them through the microscope. Can you see if a cell is undergoing mitosis, or what fraction of the cells in the slide are undergoing mitosis? Can you find it out automatically by analyzing the image? So for this, they have taken 66,000 images, and totally there are 6,000 occurrences of mitosis, and there are non-mitotic samples, so that is 151 million. So it's a highly skewed data set with only a very small number from the class of interest, and non-class examples are very high. And therefore, this is a typical problem. the problem of scantiness of data that you desire. So therefore, because you can have lots of images of normal cells, but to catch a cell in the act and when it's just dividing, and that's somewhat a rare event. So you're not likely to get as many cases of that event as of a normal cell. So to amplify the number of mitotic samples, they have taken the mitotic samples and also rotated the image, because a mitotic cell image belongs to the same class no matter what the orientation is. You can rotate it by whatever angle, it's still the same kind of a cell. So by artificially rotating the image, you just expand the number of mitotic samples. And so the data is manually annotated by expert pathologists, and then that is given to the network for training. So you see that the detected mitosis are circled in green, and reds are false positives, and cyan is a mitotic cell but not detected by the system. System missed it. So here also CNN architecture is very big. So input is 3 colors, right? And 101 by 101 is the size of the network, the size of each array. So then in the first hidden layer you have 16 maps, 16 feature maps of size again 100 by 100. But then max pooling 16 by 16 maps again, because it's a one-to-one relationship. The size reduced to 50 by 50 by using a 2 by 2 kernel size, and so on and so forth. You have lots of this convolution and max pooling stages that are repeatedly occurring. And after about 9 of them, up to 10, layer 10, you just have 2 sets of fully connected layers, 100 neurons here, and finally 2 neurons. It's a 2-class problem, which is either mitotic or non-mitotic, so it's a 2-class problem. Right, and so here in this kinds of problems where you just have 2 classes, you need to define 2 important quantities called precision and recall. Precision is also called specificity, and recall is also called sensitivity. So precision, so you have, let's look at the image on the left side. You have true positives, right, and false negatives, and false positives and true negatives. So true positives, let us say it is a mitotic case, a mitotic cell image, and the system recognizes it as mitotic cell image, then it's a true positive. Okay, so similarly, if it is a false positive, it is a normal image, the system recognizes it as mitotic cell. And similarly, you have true negative and false negative. So you compute this for number of events, right? So precision is defined as true positive by true positive plus false positive. A recall or sensitivity is defined as true positive by true positive plus false negative. So a good system should give high values of both precision and recall or sensitivity. Right, so that is indicated by this F score, which is a combination of these two, which is given as harmonic mean of 1 by precision, that is operation and recall, that is 2 by 1 by precision and plus 1 by recall. Okay, so these CNNs gave best performance compared to a lot of other traditional algorithms. You can see that here. So maybe let us, okay, we have time for one more example. The next one is using CNN, or this what I call 3D convolution CNN neural networks for human action recognition. So in action, in the previous 2 examples that we have seen consist of classifying single images. But to see an action, you need to see something in motion. You see an object in motion, and then based on that you see an action. Action here means action performed by human being. So in this case, the actions are take a few actions. Cell to ear. So somebody is taking a cell phone and putting it close to the ear. That is one kind of action. Or somebody is putting an object, at a given location. Then somebody is pointing. Okay, so how do you? So this involves processing not just a single frame but a series of frames. So how do you process series of frames and classify them? So for this case, they have taken video from a London airport, Gatwick airport, and 49 hours of video capture is done, right? And so obviously in a big video, there are a lot of people, a lot of actions going on simultaneously. So you need to isolate individuals, right? And then see what kind of actions they are performing, and if they are performing any of the three actions that we are interested in. So for that, you have to first identify the head of the person, then using that the body of the person. So we assume, so we'll take, so assume that the body is of certain size related to the face size or head size. Okay, and so you cut out that part of the image, and you track that part of the image, and you ask, like, you only scan or analyze that part of the image and see what kind of action is being performed. So cell to here, there are some sequences, some sample images. Object put is a very actually vague action, but because it can mean many things. Putting a cup, putting down a bag, etc., etc. Right, and then pointing. Pointing could be anything. So they give this as input to the network. Again, it's a CNN. But point is, in the previous case, we gave only a single image as input. In this case, they use a stack of images, so stack of frames simultaneously to the network, so that it will learn the concept of motion, right, occurring in the input video. So since it is a stack of images, right, imagine everything gets multiplied so many times in the CNN. So input has some, let's say, 7 images, right, and then each of them, 3, 4, yeah. So each image is now has now a bunch of sublayers, feature maps, a stack of feature maps in the convolution layer. Right. So for each of these 7 images in the input, you will have so many different feature maps, right? And then that's multiplied by 7. And pooling also is now done over multiple stacks of feature maps, right? And so on and so forth. So everything gets multiplied so many times because input has a stack of images. Right? And also in the previous case, a given neuron in the higher layer only looks at a window of neurons in the single previous layer. But now you have multiple images which look at different, the different frames through time. So a given neuron here looks at multiple windows, right? Each corresponding to a given frame, which is varying through time. So input is a 60 by 40 image, and there are 7 of them, as you can see here, right? Then first hidden layer has 33 sublayers or 33 feature maps, each of the same size. And so among these again, so the green corresponds to the first frame, and blue corresponds to second frame, and so on and so forth. Okay. So then you have another convolution stage, right, and so on and so forth. Now, what is interesting is they extract some special parameters so as to enable the network to extract motion from the input image. So there's a gray channel which simply consists of pixel values of 7 input frames. In addition to that, they also compute the gradient in X and gradient in Y. And let's say the input is I of X comma Y. Gradient in X is basically dou I by dou X. This will be also an image, because since I is an image, dou I by dou X is also an image. Similarly, gradient in Y is dou I by dou Y. So you have 2 images. Then they also compute optic flow, right, again in X and Y directions. So optic flow refers to global motion seen in an image because of self motion, because of the motion of the observer. That this is the original definition of optic flow. You might have seen these kinds of images in your Star Wars movie series, right, where the spacecraft suddenly goes off at close light speed, and you see all the stars coming towards you. So basically, if you have a bunch of dots in the image, and if you are going into the image, then you'll see all the points moving towards you. So if you compute the motion of each of these dots, these arrows will look as if they're going outwards. So they're as if they're going radially outwards. And then you see that the points that are close to you, that is close to the periphery, will have higher magnitude, whereas arrows which are close to the center, which is the point where you are heading towards, will have smaller amplitude or smaller length. Okay, so this is a typical kind of optic flow that you see when you are going into the image. When you are going away and looking backwards, the same thing is seen, but within the reverse, with all the arrows reversed. Now, if you are going in one direction, you look at the object outside, like when you're traveling in a train, and you see all the objects going backwards. Okay, so this is a bunch of points moving in one direction. That's translation motion. Here, all the points are moving outwards radially. That's radial motion type of optic flow. Circular motion is seen when the observer himself or herself is going in circles. So let's say you're in a spacecraft which is spinning, right? You see all the whole world spinning around you, right? And also the spinning, the velocity of each point depends upon the radial distance from the center, right? If you are close to the center, your velocity will be smaller in magnitude. Then you have spiral motion, which is a combination of both this kind of a radial motion and circular motion. So if you combine these two motions, you get spiral motion. So like this, you have different kinds of large-scale motion seen in the input image, especially in a video. So here they compute only two kinds, optic flow in X and optic flow in Y. So this is like the translation motion example here is like optic flow in X. Similarly, you can have all the dots moving in the vertical direction, which is optic flow in Y. So there's a way of computing this from a video. So I'm not going to go into that. So they have taken both optic flow in X and optic flow in Y, and they have added these images, gradient X, gradient Y, optic flow in X and optic flow in Y. So basically, this is like a spatial derivatives, both of them, and these are like temporal derivatives, optic flow X, optic flow in Y. And they augment this to the input image, because input image at any given time, the frame only captures the instantaneous state of the image, whereas these derivatives will capture the variation through time also. So they use all of this, right, and give as input to the network, and network gives overall accuracy of 90%, which is fairly good because it's a pretty hard problem, right? And yeah, so let us stop here. We'll look at more applications and maybe a couple of more applications from medicine and biology tomorrow. So thanks a lot.